We're starting the next chapter, which is on equilibrium. In this section, Equilibrium 1, we'll look at what is known as the equilibrium constant and calculating equilibrium concentrations. First, however, we need to talk about what equilibrium is. In equilibrium, we have something called a reverse reaction or reversible reaction. Some examples are given here that are very simple. For example, the evaporation and condensation of water. Water can evaporate from liquid to gas, and also that gas can reform water liquid. Another example would be the dissolving and precipitating of a salt. If you dissolve a salt in water, you can then boil the water off to get the salt back. So those are reversible reactions. Now those that are shown are actually physical changes, but you can also do reversible reactions with chemical changes as well. I want us to look at a really simple example of a reversible reaction.
Consider a wet towel hung out on a line. High-energy water molecules can evaporate and are removed in the breeze. This continues until the towel is dry and can be represented by a simple chemical equation. This is an open system. If the wet towel is left in a closed sports bag, it does not dry. High-energy water molecules evaporate and remain as vapor trapped in the atmosphere around the towel. At the same time, low-energy vapor molecules condense on the surface of the towel to a liquid. The rate of evaporation exceeds the rate of condensation until the vapor becomes saturated. At this point, a balance is reached where the rate of evaporation equals the rate of condensation. A state of dynamic equilibrium is reached, represented by a double-headed arrow. Dynamic equilibrium only occurs in closed systems.
Alright, so that is a very simple example of what we mean by a reversible reaction, and in that instance the reversible reaction was taking place forward and reverse inside the bag, but in the open system it was only taking place forward. Here's another example of a reversible reaction, this time in biology. Here we see hemoglobin, which can bind up to 4 oxygen molecules because there are actually 4 irons in each hemoglobin if we wanted to go deeper. But we'll keep it simple here. The hemoglobin binds 4 oxygens, and those oxygens are of course picked up in the lungs and then carried to the body. And then later that same hemoglobin will release those 4 oxygens to cells within the body. So that process is going to continually be forward and reverse as the hemoglobin cycles back to the lungs and then out to the cells. Some reactions, however, cannot be reversed. They do what is called go to completion. For example, if you have a strong acid, such as hydrochloric acid, and you place it in water, all of the ions will dissociate from one another. So you'll have hydrogen ions and chloride ions. As long as there is water present, those will not go back together. So here we use a single arrow to demonstrate that all of the reactants are used. So if you see a single arrow, that signifies that this is a completion reaction. We'll also see terms like go to completion in the descriptions of our problems, and that'll be a clue to us that it is not a reversible reaction. However, most reactions that occur in nature and just in life in general, they do not go to completion. And the reactants do not all get used up. Instead, the system reaches a dynamic state where the reactants are turning into products and the products are turning back into reactants. And we saw a simplified version of that in the gym bag. The water molecules on the towel were evaporating while some of the evaporated water molecules were condensing on the towel. So it's going forward and reverse at the same time. So for those types of reactions, we use a two-way arrow. This graph shows us the concentration of both the reactants and products over time in this equilibrium reaction. So you can see here at the beginning, before the reaction even started, we didn't have any of the products and we had some of the reactants, and it doesn't tell us how much. And then we started to use up our reactants. And as we did that, we were making products. Now notice the slopes here. This is an important distinction. So if you look at the slope here compared to the slope here, the increase in the products is much steeper than the decrease in the reactants. So we're using up our reactants and we're making products, but we're making products faster than we're using reactants. And the reason for that in this case is this coefficient 2. As the reactants are used, every time you use one of these, so this goes down by 1, you would make 2 of those. So that would go up by 2, down by 1 and up by 2, and so on and so forth. So the slope down here of our product should be double our reactant, and of course in the opposite direction, because the reactants are being used while the products are being made. As the products increase, some of the products start to make reactants, and then the reactants continue to make products, but we see that the change is slowing down, and slowing and slowing, until there's no change in the concentration at all. And when we reach that point where there's no change in the concentration, it looks to be about right here, we say that that is the point at which we've reached equilibrium. Now at this point, you still have your reactants making your products and your products making your reactants, but now they're doing so at the exact same pace. So the concentration of neither of them is changing. So this is making your product at the same time your product is making your reactant. It's as though it's going 2 steps forward, 2 steps back, 2 steps forward, 2 steps back. So the concentration of the two species remains constant over time once you reach equilibrium. This chart shows the rate of reaction. So at the beginning, our reaction rate is faster for our products only because it has a coefficient of 2. And then the rate for our reactants is decreasing at half that amount. So the rate for the products increases, the rate for the reactants decreases until they're both occurring at the same rate. They do not have the same concentration. This is just saying the rate of the forward, which is shown by the product, or excuse me, shown by the reactant up here, and the product is now the same. So again, this, where we see this line come together, this is our rate from the y-axis. So at equilibrium, if we take a look back at the previous slide, we can see that the concentrations are not the same, but they do stay constant. But the rate of reaction of the forward and the reverse is the same at equilibrium. So what is chemical equilibrium? This requires a forward and reverse reaction, and these reactions are both taking place at the same time, the forward and the reverse. And the rate of the forward reaction is equal to the rate of the reverse reaction. Because the rates are the same, it's going forward, reverse at the same rate, the concentration of the species is constant but rarely equal. They're just staying constant, but they're rarely equal to one another. Chemical equilibrium has to take place in a closed system, like we saw with the towel. If it's open to the atmosphere, then those molecules will leave and they won't be there to complete the reverse reaction. So we need a closed system, we need a reversible reaction, and we're going to get to a point where our rates are equal and our concentrations will remain constant, but not equal. This is an example of a reversible reaction, just really generic. We have A and B are forming D and E as products, but of course D and E are also forming A and B, as the reaction can be in the reverse as well. And then we're just using some tiny letters there, lowercase letters, to show coefficients. Those could be any numbers depending on what the species were to balance the equation. We can calculate what is known as an equilibrium constant. And that is a value that doesn't change for that reaction unless the temperature changes. This value will stay the same for that reaction, and it kind of gives us an idea of when we get to that equilibrium point and those concentrations stay constant, do we have more products or more reactants, and what is the ratio between them? This equilibrium constant was discovered, and it is known as, let's see if I can type it out here for you. This is based on what is called the law of mass action. So all this says is when we get to equilibrium, there's going to be a ratio of products to reactants that's going to stay constant. And if we make any changes to the system's going to adjust to get back to the same ratio that it is at equilibrium. The only thing that will change this ratio is the temperature. And of course, it will change if the system is open. But as long as the system stays closed, we'll keep this same equilibrium constant. And this is shown by a capital K. Now, how is this calculated? You put the product concentrations on the top. So we're using the values of concentration here, which is molarity. Remember, moles per liter. Those values would go in the brackets. And then your coefficients become your exponents. So we have the concentration of species D raised to its exponent, the concentration of species E raised to its exponent, over your reactants, their concentration raised to their exponent. This formula here is called the equilibrium expression. Again, it shows us the ratio between products and reactants. This K value, if you see capital K, is always calculated the same way, products over reactants. And they'll put little lower cases there to be more specific. So if you see a little lowercase c, that's telling you that we're talking about concentration. So we use those brackets to refer to concentration. Alright, we'll see lots of examples of this as we move forward. Jot down any questions you have about that as we move along. Here's a chance for us to write the equilibrium expression. Now, this often causes some hiccups, so I want to clarify here. If we're writing the equilibrium expression, then that is when we're going to write these formulas for our products and reactants into the equilibrium expression. We don't want to use numbers yet. We want to use formulas in our equilibrium expression. Right? So for the equilibrium expression, we're going to write K or KC or KEQ, whichever one you're using, equals. Then we'll put our product on the top in the bracket, and its coefficient becomes the exponent. Then on the bottom, we've got our reactants, and we put those in brackets because we're using KC for concentration. And they don't have any exponents because their coefficients are 1. Oftentimes on the AP exam or on a test or something, they'll ask you for the equilibrium expression, and it's this simple. Products over reactants, put them in brackets, raise their coefficient. One thing you have to remember is to write a mathematical expression, you have to have an equal sign. So in this case, you always write K equals. You can put the C or you can put EQ if you're using concentration values. Alright, here's another example where they ask us to write the equilibrium expression, and they give us the answer actually. They want to teach us something here. So we have products, but notice they didn't include nickel. So they just have the carbon dioxide. And then on the reactant side, they don't include the nickel oxide. So the nickel and the nickel oxide are correctly left out of the equilibrium expression. And what do those two things have in common? They're both solids. So solids, it's a rule to remember, are left out of the equilibrium expression. Okay, why is that? Okay, let's think about a reaction. Here we have a piece of nickel oxide originally as a reactant, and then as the reaction moves forward to the products, some of that nickel oxide is being used. So its volume is going down. However, if you think about its concentration, the concentration is measured in moles per liter. So the liters, the volume went down, but so did the moles, right? So the moles per liter, or the concentration, hasn't changed. Both pieces of nickel oxide would have the same density, so both of them would have the same particles per liter. So therefore, the concentration of a solid does not change. Sorry, I didn't mean to mark through that. The concentration of a solid does not change. So when we put those brackets, we're saying the concentration of that species, and a solid's concentration doesn't change. So we don't include solids in the equilibrium expression. All right, here's another example. Write the equilibrium expression for this reaction. So Kc equals products on the top, reactants on the bottom, raised to their coefficient. What do you see that they left out here? They left out the water. Water is a what? A liquid. Liquids, just like solids, are left out of the equilibrium expression. So solids are left out, liquids are left out. What do we include? We include gases, and we include things that are aqueous, meaning they're in liquid. They are not liquid themselves, though. So think about when you put salt in water, the salt is aqueous. It's in the water, but the salt is not a liquid. Okay, the water is the liquid. So we don't include liquids or solids, but we do include gases and aqueous substances in our equilibrium expressions. All right, here is another explanation for that. If we're talking about liquids. If you add or take away a small amount of water in a reaction that takes place in an aqueous solution, that doesn't affect the concentration of the water. It affects the concentration of the stuff in the water, but it doesn't affect the concentration of the water itself. Okay, so liquid concentration doesn't change, and neither does solid over the course of a reaction. So we're going to include gases and aqueous species, and we're not going to include liquids or solids when we write the equilibrium expression. For gases, sometimes we'll calculate or write an expression for what is called a Kp. And what that refers to is the equilibrium constant in terms of pressure. So the P stands for pressure. To write that, we're going to do the same thing that we do with concentration. Products go on top, reactants go on bottom, raised to their coefficient. But instead of brackets to signify that we're talking about concentration, we're going to use capital P's to signify that we're talking about the pressure, and then we'll make the substance a subscript. So here, when you see, for example, PD, that means the pressure, we call that the partial pressure of substance D. The partial pressure of substance E. We call it pressure because all these things are in the container together, and they're all going to be hitting the sides of the container. And then we say partial pressure because we want to talk about the pressure caused just by D. So that's the partial pressure of D, the partial pressure of E, the partial pressure of A, the partial pressure of B. When we say partial pressure, we're distinguishing from total pressure. Total pressure would just be everything in the container, but we just want to talk about the pressure from that substance. So Kp is the equilibrium expression in terms of pressure. It's set up just like Kc or KEQ, products of reactants, raised to their coefficient, leave out solids and liquids, just like we said earlier. The only difference is we're going to use this sort of pressurization instead of using the brackets for concentration. Right? Here again to clarify what we mean by partial pressure. So the partial pressure of a gas is when the gas is in a system, so it's there with lots of other gases, and we want to focus on the pressure exerted by that specific gas. If we add up all the partial pressures, that's going to tell us what the total pressure of the system is. But in this case, we're just concerned with the partial pressure of that species. If you have 1 mole of some gas and 1 mole of another gas, they're going to both exert the same pressure. But if you have 2 moles of a gas, it's going to exert twice as much pressure. So the amount of gas is really what determines the pressure. It doesn't matter what kind of gas it is. You can convert between Kp and Kc if you know one or the other. So remember, Kc refers to concentration and Kp refers to pressure. But if you know one of the values, then you can convert to the other one using this equation. Kp equals Kc parentheses RT, where R is the gas law constant, and you see that there. So that number would just be plugged in the equation for R, along with all its units. T is the temperature in Kelvin, because R has Kelvin as a unit, so they can cancel. And then the N value is known as the change in moles. Because we're talking about pressure versus concentration, what we're concerned about when we say change in moles is the moles of gas. So to find this delta N, you would count how many moles of gas were in your product just by looking at the balanced equation, and how many moles of gas were in your reactants. Again, this comes from, let's make ourselves a note here. These numbers that we're talking about here are from the balanced equation. Oftentimes on the AP exam, they're going to give you this equation if they want you to solve for any of these variables, but delta N, a lot of people don't know how to figure it out, and so the AP exam will often give you 1 point just for figuring out what delta N is, and then 1 point for finishing out the calculation. Alright, so let's look at an example here. They want us to find Kc and Kp for the following system, and they give us a temperature. Now the reason the temperature is important is only because as long as we stay at the same temperature, then the K value should stay the same. The Kc value will stay constant and the Kp value will stay constant. If we change the temperature, we would have to redo these calculations and find a new value for Kc or Kp. Alright, so whenever we have an equilibrium problem, the first thing we want to do is write the equilibrium expression. So no numbers to start out. Just going to write the expression. So products of reactants raised to their coefficient. Now here we decided to start with Kc. And the reason is because the numbers they gave me were concentration values. So I need to find Kc first because that's the type of data that I have. So from here, I'm going to take the numbers they gave me and plug them into the appropriate spot. So they told me the concentration of HBr, they told me the concentration of H2 and Br2. And it's important because they said those were at equilibrium, so I can use them in the equilibrium expression. I calculate Kc here, and I'd find it to be 59. So now I can find Kp using that equation. We said that Kp equals Kc RT to the delta N. We know Kc from step 1. We know R from what was given to us on the previous slide, that 0.0821. We know the temperature. Remember, they gave that to us in the problem. We'll change it to Kelvin by adding 273. But what about delta N? That's moles of gas in the product minus moles of gas in the reactant. So let's look at our products first. How many moles of gas do we have over here? 2 HBr molecules, so 2 moles of gas. Minus, how many moles of gas do we have over here on the reactant side? 1 of H2 and 1 of Br2, so again we have 2. So our delta N value is 0. So our exponent right here is going to be 0. Alright, so we'll use that to calculate Kp. So we plug in our numbers. Anything raised to the 0 is 1, so that RT raised to the 0 turns out to be 1. So Kp also turns out to be 59. So this is a clue or a shortcut. Anytime your delta N is 0, so you have the same gas on the reactant and product, your Kp will be equal to your Kc. Alright, so let's make a note of that. See if they'll let me type here for you. Here. So if I can't type a delta very easily here, but if N, delta N, you know, turns out to be 0, then Kp equals Kc. So that is a popular multiple choice type question because you're like, crap, I can't do these calculations without a calculator, but you don't have to. If your delta N turns out to be 0, then your Kp and your Kc value will be the same. Alright, so we'll stop there and we'll pick back up next time on the next slide talking about what these numbers mean once we calculate them.